And hi there. My part of the presentation involves the mathematics of origami, and I'm going to cover the special products which are in origami covered with the hen and the boat. We're also going to talk about Pythagorean theorem in terms of the design of the folds and the 3D figures with respect to volume, surface area, and other measures you can take. And I use GeoGebra to prove these. So I'm going to begin with the hen. And so if you notice in the hen fold, you'll notice that the pink piece of paper is representative of an origami square. And if you take heed of or pay attention to the lettering up here, you notice that I have areas of separated rectangles and squares respectively. And so the area of ABCD, which is the entire pink area, minus the area of APOS, which is this little slab right here, APOS, minus PBOQ, which is this little square at the top, right? Minus P, let me see what it is. It's OQRC, and that's this little slab, minus the last piece down here, which is SORD. And so all of this together comes to create our a squared minus 2ab plus b squared formula. Up here, this is basically the calculations I just described. And so if you want to see the actual fold and how it ends up being the hen, you can actually click on this link, YouTube link, and it will take you to a very nice explanation and demonstration of how we fold it. It's actually very simple. It's very much related to the boat, obviously. The boat is the other special product where we have a plus b squared, and so this one is a little bit easier not only to fold but also to describe. So the product of the special proof, you could see it just in the areas alone. So area 1, which is a squared, plus two areas, which are area 3 and 4, or the ABs, so how we end up with 2AB, and then plus, lastly, the area B squared. And so once again, I provided you a link to a demonstration on how to fold this, and it's actually simple. It's about 4 folds, and you're done with this. And this is very helpful in helping students see the big picture with respect to FOIL. They always ask, where does the middle term go? And I try to explain and explain and explain, but they don't see it. With this explanation, they do see that there is a 2AB provided in there. The Pythagorean theorem, another very easy fold, which if you can see, obviously the small sides, the small parts here, where I'm moving my cursor, are the A values. And the longer, slightly longer sides are the B values. And you see that happen in each of these green areas, which are right triangles. Notice that once you fold these, you'll end up with C squared, which is the main center part. So A squared plus B squared equals C squared, and you'll see that in the fold. It's actually very cool. Check out this link. Very nice 3-minute explanation, very easy to solve. Where I want to spend the bulk of my time is here. And this is creating origami in GeoGebra and its use when teaching. So I'm going to I started with tetrahedron, then I did a rectangular prism, pentagon, hexagon, heptagon, octagon. You can go as far as you wish. And I'm also going to demonstrate how we even arrived at these creations. So let me start with the tetrahedron. So if you notice, the first thing you notice is I have it laid out flat. And this is a great way to explore. Just explore to your heart's content. As a teacher, you can change the length of the sides, have the students find a particular length. But as a fold, if you look at just the net of what's here, you basically have one very large equilateral triangle. If you'll notice, the sum of these two smaller triangles is the same all around. And what I have in the center is yet another equilateral triangle. And it's a simple fold. It's fold over from either direction. So if you'll notice, I can actually create that into a prism, three-dimensional. And as you look at the different sides, there's the bottom, and just have fun with it, exploring the different edges and whatnot. And so what is really interesting is here, I actually took the tetrahedron out. So there is your tetrahedron is sitting right in there. It's inside the figure, if you could see. And what I also did was I took my time calculating the volume and surface area using various parts that are found as we explore the three-dimensional tetrahedron. What I also like about this feature is once you displace the net and you show them what it looks like on the computer, they want to both do it with the paper and they also want to do it on GeoGebra. So this was actually a very beautiful lesson and worked out swimmingly as students went ahead and explored these. Just a side note, I mean, I'm actually considering a lesson plan where I'm going to use this to maybe just for fun on a whimsical day after exams, have them create Christmas ornaments. In this case, they're going to create obviously a tetrahedron, but if you add two more sides, you can actually create three-dimensional stars and all sorts of neat activities. So math related here, obviously they can explore surface area and the volume using either formula. As you can note, I actually provided the formulas and the calculations here. You can also obtain these from the actual GeoGebra program. So you do have that ability. We have surface area here as well. And so we are exploring the formulas. Now, the reason why this would be very important in a classroom is simply for not only math knowledge, but the preparation of SAT or standardized testing, because they do ask them these questions. They ask them questions with respect to surface area volume of three-dimensional figures, and they'll omit one of the variables and they have to solve for it, and this way they could see everything as you're working the question out, which is really phenomenal. I know that three-dimensional geometry is not really covered that often at the 9th or 10th grade level, unless it is a geometry class, but normally geometry is taken at younger years, I would assume. I know that the students that I tend to see are 11th grade students, and they're registered in MAC 1105, which is college algebra, or MAC 1140, which is pre-calculus, or they're in trigonometry, MAC 1114. So, like I stated, I mean, even in differential calculus, which is another course that I teach in this term, and I have students asking me questions about FOIL. So if we could use the math in GeoGebra to demonstrate that, that would be like with the boat or the hen, with that type of manipulation, that'll be helpful to them. The other figure that I did also include there was the quadrilateral. So let me open from here, probably be quicker. So I have several of these. I went nuts, just enjoying the moment. I'll go to edit so I have a little bit more control. So in this case, when you click on the link in the PowerPoint, it'll bring you to this shape right here, which is a three-dimensional rectangular prism. Again, easy fold. You could actually measure out the angles here with a straight edge and compass. Fold the paper 3 ways, hot dog wise and hamburger wise, with the top remaining on one of the ends. And then you can literally just show them how to fold the paper and just look at this from various perspectives, whether it's from, the perimeter or just a simple area or volume or surface area of this particular figure. This is great practice, and again, another lesson that my students enjoyed tremendously. So this is quite fun. So the net is actually like your paper, by the way. Let me show you a quick demonstration of how easy this is to create. So I'm going to go ahead and actually do this live with you. And this is a ton of fun. And so we're in 3D, and what we want to do is within 3D, let's select, let's go with regular polygon. All right, I'll select 2's. And let's say I want, hypothetically, let's do the Pentagon since the pentagonal size. So if you notice, we have a 5-sided figure here, and once you do that, just go to extrude to prism, click on the figure again. How tall do you want this figure? Let's go with 6 for altitude. There you go, nice long figure. And the other thing you want to do is you want the net. You click on it again, by the way. Okay, and so what you see down here in brown, looks like brown, this is the actual base of your figure, which you can actually do with paper. You just have to remember you're going to need a compass and a straight edge to make sure that all of your angles are 72 degrees out here. How you find that? Simple. You can have the student simply click 1, 2, 3 at 72 degrees. If I click here again, 1, 2, 3, the center angle is what I'm looking for. All right, and you'll see that will give you 72 degrees respectively. Same thing here. I click on this angle, and there should be 72 degrees here. Let me do that again because it did not take. So yeah, so that's all you need to do. And what you need to also then share is within this, I have one already made. So let me go to File, Open. I think it's this one. And if you look at this one I'll just do Pentagon 3D shape. This is very interesting to explore for students because you can look at the apothem, which you're going to need anyway to find an area for just a simple pentagon, one-sided pentagon. If you wanted to discuss that with them, you could talk about how to find the apothem. You can also talk about how the size of a pentagon, which is 5 minus 2 times 180, which is 540 degrees, tells us that these angle measures in here are 108. Notice that the exterior measure is 72 because the straight line has to be 180. That's how we know that that's 108 on the inside. In case you want to check it out, you just go back to GeoGebra and click on the angles, and you'll get your interior angles. What else did we do with the same thing? It folds just like a piece of paper. Oops. If I hold and click, give me 1 second. Let me stop being a nerd. There we go. You can see it go and click. There you go. And now you can even see your creation of where the apothem sits and the edge as well, which you'll need for the formula. So, and I do have a slide on the pentagon. Just like with everything, there's a formula. I give you the formula, so I'm going to open it back up so you can see it clearly. Now you can see the formulas here. You have the surface area and volume formulas. Further up in the presentation here, in this particular slide, let me see if I can move this up. You can see that I discuss where the angles come from and so on. So very good stuff to use as a really good activity to physically explore with paper, the creases and the creations of these. But the main idea, however, is you have to remember to measure out these exterior angles to make up for what's left of the interior angles. So, really good project, really good activity. These are links to all of them, so you can always play with these. And again, I did pentagon, hexagon, heptagon, octagon. And really good material to explore angles, interior angles, exterior angles, angle formula. Probably in one problem you could likely explore at least 5 or 6 questions that are on the SAT alone. There we go with the 5/2 times side times apothem. So they call these edges. So this is what I was referring to in prior. Lisa's going to continue by discussing some technologies that are inspired by origami. And these are just a few that we have found as a team. And this video is amazing. I would ask you to please take a few minutes, look at this video. It is extremely informative, and look at how simple that looks and how it unfolds. And so you understand that this is how we created that. Amazing. Just amazing. Because imagine the solar winds that they have to eventually hold off to. So there are many technologies. I encourage you to watch that. And I think this will be fun for you. All right. And I'll leave the rest to Lisa.